We're going to begin working through the AP style questions for homework number 7 here. So to start, I have a system of two blocks, and it's frictionless, being accelerated to the right by some pulling force F. And I want to know the magnitude of the tension in the string connecting the two blocks. What I'm going to actually do first, though, is I'm going to treat the two blocks as a system, treat them as one object with a mass of 3 kilograms. Okay, for that object, we have this pulling force going to the right. We also have normal and gravity, but we don't actually care that much about those two in this situation because we're going to be concerned with the horizontal acceleration of the object. And that is the way that it is accelerating. So I'm going to set up my F equals ma, and I realize I can't get an actual answer here, but I can find that F is equal to 3a. So F over 3 equals my acceleration. So that's the acceleration of each of the blocks. I'm now going to go ahead and just focus on the forces acting on that 1 kilogram block, because that's the object that has tension causing it to accelerate, and that's what I ultimately want to find. So for that 1 kilogram, we have the force of tension. We, of course, have the normal force and the force of gravity, and we found that this object is accelerating at a rate of F over 3. That's what we found with our first part. So setting up my F equals ma once again, I have that force of tension is going to be equal to the mass, and now it's just the mass of that single block, times the acceleration F over 3, which means my force of tension is just F over 3. So our answer here is going to be E. Moving on to this next one, we have a situation where 3 blocks are being accelerated to the right, and there's 3 different strings connecting the blocks, right? So we have C connecting the first block, B is in between the first and second, and A is in between the second and the third. We want to know which string needs to be the strongest, which one needs to be able to handle the most amount of force without breaking. So I'm going to once again use the idea of a system here to go ahead and set this up. So I'm going to think about string C. I'm just going to call it FC. That needs to be able to accelerate 3m plus 2m plus m. All right, all 3 of those blocks together. We, of course, have friction going back to the right, Fn and Fg. Okay. If we think about string B, all right, the force from that is accelerating 3m plus 2m. We, of course, have friction going back to the right yet again, normal and the force of gravity. And lastly, string A is just accelerating that 3m block, normal and gravity are acting on it, and friction yet again. Okay. So we want to know which string needs to be the strongest. Well, that's going to be string C here, okay? Because string C ultimately is accelerating the greatest amount of mass. All right, you might be tempted to say string A because it's connected to the 3m block. However, keep in mind that string C accelerates the 3m, the 2m, and the m. When we think about them as a system, okay, we can see that string C actually accelerates the greatest amount of mass, or pulls on the greatest amount of mass. B pulls on just the 3m and the 2m, and A, even though it's pulling directly on the largest block, is really only pulling on a total mass of 3m. So the answer here is going to be C. For this first question here, we want to go ahead and draw the forces acting on the 2 boxes shown in this diagram. So here I have my 2 boxes, big M and little m, and I'm going to start by thinking about what forces we have. We, of course, have the force of gravity acting on each, so I'll call that Fg1 and Fg2, just to distinguish between the 2 of them. We have this pulling force here, that's just F, that force right there, so I'm just going to leave that there as F. We also have normal force. We have a normal force from the ground pushing up on box with a mass of m. There's also an additional normal force, okay, that pushes up on box with a mass of little m, and that really comes from the bigger box here, m. So I'm going to say that this is our second normal force. I'll call that Fn2, and then I'm going to call this Fn1. Because this bigger box is pushing up on the smaller box, it means the smaller box is also pushing down on the bigger box, which means Fn2 is also a force that goes down on the box with a mass of m. We know that they're being accelerated here to the right. Okay, so I'm going to draw my acceleration in both cases going off to the right. And I'm going to think about first what force actually accelerates that smaller box. And this might sound a little bit weird, but the force that actually accelerates that smaller box is the force of friction. And it's the force of friction that exists between those two boxes. So I'm going to call that the force of friction 1. Okay, there is friction between m and little m, okay, and that's what ultimately prevents little m from slipping. Okay, so it is going to be static friction. That means, by the way, that there is a force of friction, that same force of friction 1, going backwards on box m. Okay, and I want to be clear, that is the friction between these two surfaces, because in addition to that, there's friction that exists between these two surfaces, big M and the floor itself, and I'm going to call that the force of friction 2. So we do have a lot going on there. Okay, we have, like I said, force of gravity on each box. We have normal force from the floor, and then the normal force that exists between the two boxes. All right, we have the pulling force, or the pushing force, of course, that's pulling the box with a mass of big M. All right, and then there's two forces of friction. For this surface here, that's a kinetic friction because the bigger box is sliding along the surface, and then the force of friction here, that's static friction because this box is not sliding. All right, and that's what that FF1 is. Keep in mind, though, that if the bigger box M pushes the little box to the right, that means the little box is pushing the bigger box to the left. Second question is, what is the acceleration of the two boxes? I could take these two free body diagrams that I just had, but I think the easier thing to do is actually just to treat this as a system. So I'm going to do that very thing. I'm going to think about the forces that are acting on the combination of the two boxes, and that means it's going to be F, okay, that force pulling it. We're going to have the force of kinetic friction between big M and the floor, which really was FF2. That's what we had called it before. All right, and then we're going to have a normal force, all right, pushing up from the floor, and the force of gravity. So I'm going to go ahead then and set up my max and my may. I'll start in the y direction. I have the normal force minus the force of gravity acting on that system. That's going to be equal to 0. So I can say that my normal force minus the total mass of our system, m plus m, times g, is just equal to 0, which means that my normal force in this case is going to be the sum of the masses, big M plus little m, times g. I'm also going to go ahead and set up my x forces, all right, thinking about what forces I have in the x direction. And so we have that pulling force F minus the force of friction is equal to the mass, and we're going to once again do the total mass of our system times our acceleration. I can substitute in mu k times my normal force for the force of friction, and that is going to be equal to the total mass of our system times our acceleration. And then I'm going to sub in this normal force that I found over here in for the normal force in my x equation. So it's going to be m plus little m times g, and that's equal to the total mass of our system times the acceleration. And I'm going to divide by that, and I find that the acceleration is going to be f minus mu k times big M plus little m times g, all over the total mass of my system, and there is my acceleration. For this third question here, it asks, what is the force that ultimately makes the box with a mass of little m accelerate? And I look back to my free body diagram, and I see that it's this force of friction here. Okay, that force of static friction that acts between the box with a mass of big M and the box with a mass of little m. And the reason for that is two things. Number one, it's the only horizontal force, but more importantly, that box with a mass of little m wants to stay still when the box with a mass of big M is accelerated. So what force makes it move along with that box? That force ends up being static friction. It wants to stay still. It wants to basically stay in place while this box moves forward, okay? And the force that actually keeps it moving with the system, okay, that acts opposite the direction it wants to go, it wants to stay at rest, that force is the force of static friction. For D here, I want to find the maximum possible acceleration of the boxes before the small box slides off. So I'm going to think about the forces acting on that smaller box and set up my max and may. So I just moved this free body diagram down here. Okay, now I'm going to set up my max and may for the smaller box itself. And so it's going to be Fn2 minus Fg2 equals 0 in the y direction. So that means that Fn2 is just equal to mg, the mass of the smaller box, times g. And in the x direction, okay, some of the forces in the x, the only thing I have is that force of friction, force of static friction in this case, which I'm calling Ff1. And that's going to allow me to solve for that maximum acceleration, A max, which is different than this acceleration here. That wasn't necessarily the maximum. What I can do, though, is I can say that the force of friction is going to be equal to mu s times our normal force. In this case, force of friction is equal to mu s times our normal force, not less than or equal to, because of that word there. Okay, that means that if our friction is at a maximum, our acceleration will be at a maximum, and so we can say the force of static friction equals mu s times our normal force rather than that inequality there. And so that's going to be equal to m times that maximum possible acceleration. I'm going to substitute in that normal force that I just solved for, so mu s times mg is equal to m times a max. The m's cancel out here, and I find that my maximum acceleration is just going to be equal to mu s, that's static coefficient of friction, times g. All right, we have another free response question here, and this is an experimental design one. So we have this device over here, which is known as an Atwood machine. It just consists of two masses that are connected by a rope over a pulley. And this was something that was historically used to study accelerated motion. So we want to be able to determine the acceleration due to gravity using this Atwood machine, a stopwatch, and a meter stick. So the first part is our typical experimental design, going through what we would actually do. Our second part is talking about how we would analyze the data to determine the acceleration due to gravity. What I'm going to do is I'm going to start by drawing my free body diagram, part 3 here, and actually doing part B, and then I'm going to go back and do these two parts, because sometimes it's easier to write your procedure knowing what information you need rather than the other way around. So let's think about the forces acting on the objects. Okay, so we know that each object has a force of gravity acting on it, so Fg1 and Fg2. And we also know that each object has a force of tension, and that force of tension is going to be the same on both objects. In terms of the acceleration, we're told that m2 is greater than m1, which means mass 1 will accelerate up, and mass 2 will accelerate down. So there's my free body diagram for both objects. I'm now going to set up my F equals ma for each one. Set up my F equals ma here. For the first object, I'm going to have Ft minus Fg1 equals m1a. So I can rewrite that as Ft minus m1g equals m1a. For the second object, I'm going to say Fg2 minus Ft equals m2a, again making the direction of the acceleration be positive. So m2g minus Ft equals m2a. And now I'm going to combine those equations. So just slide this one over here and add those two equations together. As always, the Ft's are going to go ahead and cancel out. And what I'm going to be left with for my overall equation is m2g minus m1g is equal to the sum of the masses, m1 plus m2 times a. Now I could have gotten that same equation if I had set this up as a system and only thought about the forces acting on the system, which in this case would just be Fg1 and Fg2. Fg2 going in the direction of the acceleration and Fg1 going against it. So if we had set it up that way, it would have worked out the same. Now, I ultimately am looking for g, right? That's what we're solving for here. The whole idea of this experiment is to determine that acceleration due to gravity. So I'm going to rearrange this equation to solve for g. So on this left side, I'm going to factor out a g. So m2 minus m1 times g equals m1 plus m2a. And when I solve for g, I get that g is going to be equal to m1 plus m2 times the acceleration of my system, divided by m2 minus m1. Thinking about that equation and what things I know the masses. All right, it says up here that all the masses are known. So that means the thing I need to figure out now is the acceleration. So how am I going to get the acceleration of this system using the equipment that I have? I have a stopwatch, I have some meter sticks. Okay, I can get the acceleration of the system using good old kinematics. So I'm going to set that up as well. Okay, so things that I can measure using that equipment. I can measure the displacement using the meter stick. I can measure the time using the stopwatch. And to get that third variable I need to be able to solve for something with kinematics, I'm just going to say that my system starts at rest, and then I know that my initial velocity is 0. Solving for the acceleration using my kinematics information, I'm going to set up my delta x equals VIT plus 1/2 AT squared. That initial velocity term goes away because my initial velocity is 0. And so what I'm left with is delta x equals 1/2 AT squared. Rearranging for a, I get 2 delta x over t squared equals my acceleration. So now I have a method that I can use to solve for my acceleration, which ultimately allows me to solve for g. I know my displacement, I'll know my time, okay? I'm going to take that acceleration, plug it in over here, and then I know everything. So I'm going to finish up part B here, just writing a few sentences about what I would actually do, and then we'll go back and take a look at part A. So here's what I would say just to supplement all this math and derivation that I've just done. I would say use the displacement and time that were measured, all right, and we'll talk about how we have to measure those when we go and discuss our procedure in part A. So use displacement and time that were measured to solve for acceleration. Okay, you can even reference the equation that we just derived, that a is 2 delta x over t squared. Okay, and then we're going to use the acceleration and the known masses to find g, the acceleration due to gravity. And once again, you could go ahead and reference that specific equation that we derived above, and then it's very clear exactly how you're going to get that acceleration due to gravity. Having these two sentences in here is key. It does help to supplement your explanation here, and it very clearly says describe how to analyze the data. Just having a derivation, just having formulas is not sufficient. Okay, going back now to the beginning part of this question with what quantities we measured and what procedure we would use. Let's first of all look at what we ultimately needed to measure to do this. So what we ultimately measure, if we look at our kinematics equation, is we need a displacement, so displacement of the masses while they're falling, and we need a time. So those are the two things that we need to measure. In terms of a procedure here, I would start by measuring the distance that mass 2 is above the ground. Okay, we know it's connected to the ceiling, so I think we can just measure this distance in here that mass 2 is above the ground. Next, we want to talk about what we're actually doing to complete a trial. So release the system from rest, that's a key point. We need to have no initial velocity. So release system from rest. And then I would say measure the time it takes for mass 2 to hit the ground, because that's the one that's accelerating down. It does include this line here about be sure to include details on how to reduce experimental uncertainty. So the easiest way to do that is repeat this procedure multiple times. Okay, and then we're going to just ultimately average all those quantities. And so there we have the first two parts. I think it's easier to go about doing these problems this way. Sometimes it's tough to kind of think through the entire experiment in your head. So doing B first, I think, is a really useful tip. Thinking about how you're actually going to solve it mathematically, and then going back and thinking about what procedure you need to get that information. So there you have it, another experimental design question.